So the next speaker is Professor Enrica Pirozzi.
Yes.
Sorry.
Yes, yes.
Sorry.
No, it's right.
Also from Napoli, and she's going to discuss a fractional stochastic Gompertz-Type model induced by Bernstein functions. So we had a lot about Bernstein. So please, you have 25 minutes and then 5 minutes for questions. Thank you.
Okay. Can you see my screen?
Yes, but make it a full screen, please.
Yes, I hope to. Now?
Perfect.
Okay, thank you very much for the introduction. And first of all, I also want to thank a lot to the organizers for kind invitation and for giving me the opportunity to talk about some recent results obtained studying with Giacomo Ascione and about a fractional stochastic Gompertz model induced by Bernstein functions. I give some details about previous fractional version of Gompertz models, also to give a motivation of such work, and then I explain our first attempt to give a fractional generalization of Gompertz models, and then a further step of generalization by using Bernstein functions. First of all, I want to recall that the Gompertz curve is the solution of this nonlinear Cauchy problem, in which alpha and beta are dynamical parameters, and x0 is the initial population density. The well-known solution has the form indicated at the bottom, and the carrying capacity is its limit over time t involving all parameters. First, another way to write the Cauchy problem is to set yt equal to the logarithm of ratio between xt and x0 in order to obtain two differential equations involving function xt and yt. And starting from this, a first attempt to construct a fractional Cauchy, a fractional Gompertz curve was due to Bolton some years ago. Following their strategy, the fractional Caputo derivative is in place of the classical one with the fractional order mu in 0, 1. In such a way, the fractional Gompertz curve was the exponential of this y nu t function. Specifically, y nu t involve a Mittag-Leffler function, and the fractional Gompertz curve is the exponential of such a function. A second attempt to give a fractional Gompertz model in the deterministic context again was to adopt the yt directly in this specific form and to rewrite the above problem in more compact way, because in such a way Frunzo and Tal do a substitution adopting the Caputo fractional derivative respect to another function. Specifically in this case, the another function is the exponential beta t. And the improved, so the name from Frunzo et al. Improved fractional Gompertz curve is the function that is a Mittag-Leffler function of this one. In the stochastic context, the Gompertz process is the xt solution, the process solution of this kind of SDE, in which Wt is Brownian motion and alpha and beta plays the rule of group parameters. The strategy to solve this SDE is to start with the process yt equal to the logarithm of the ratio between xt and x0. In such a way, applying the formula, we obtain this SDE that is the SDE of Ornstein-Uhlenbeck process. we recognize that the solution has this expression, and it is Gaussian process. At the end, the Gompertz stochastic process is the log-normal process obtained in this way. The link with the deterministic Gompertz curves is that the mean of a YT process solve this equation that is the second in the original problem, and the median of xt in the process is the Gompertz curve obtained, as we know, as the exponential of the mean of its logarithm substantially. We want to generalize this approach. We want to construct the stochastic fractional Gompertz model and to unify the vision of Boston and Frunzo, already cited. So we, following Almeida, we recall the fractional integral respect to psi function. That is exactly this one. We have already seen during this workshop this notion. And recall that if psi t is the identity, we achieve the classical fractional integral. The Riemann-Liouville fractional derivative respect to psi function is defined in this way. We require psi in C1, 0, infinite, and with the derivative different from 0 for anything greater than 0, and for any suitable function for which it is possible. So again, note that if psi t function EU is equal to t, we again obtain the classical Riemann-Liouville fractional derivative. And as you can see, there is this relationship between Riemann-Liouville fractional derivative and the fractional integral just presented here, respect to psi function. Also, Caputo fractional derivative respect to psi, and denoted here in this way, can be defined using psi function in the kernel integration kernel, and the relationship between Caputo derivative and the Riemann-Liouville derivative is similar to the already known for the classical case when psi t is the identity substantially. So under suitable assumption, we know that it is well posed the fractional Cauchy problem. And in the spirit of Osler, we can show that also a chain rule holds for these operators. This is a very useful rule. Take in consideration that FT is obtained as composition of G function and suitable G function at psi function. Is very important, this rule, because by this we can solve the relaxation equation, and it is sufficient to recognize that by using the eigenfunction of Caputo derivative, that is a Mittag-Leffler function, the solution of this problem is obtained exactly composing the Mittag-Leffler function with the function psi in this way. And how we can proceed for the construction of fractional stochastic Gompertz? We start considering y nu t written in integral way, so as the solution of this fractional integral equation, in which we involve now the fractional integral just presented, and an additional G process, FT adapted Gaussian process, that we call the noise process substantially. Considering the set of FT adapted Gaussian processes with almost surely continuous paths, and GR that is the set of the same process for which we have also almost surely are all the continuous paths, we prove that there is and is unique the solution y nu t of such integral equation, and under if additive process G is in the same set, we have also the new Helder continuous paths for the solution process. Limiting to the centered process GT, we can also prove that the mean of such a process solve this fractional Cauchy problem as considered before by Bolton et al. And about the choice of GT, I can say that is substantial important because in the real application, the covariance of such a process is affected by the variance of G process. But the natural choice at this point, or a first step to choice of G, is to consider this kind of process that is Levy fractional Brownian motion, because in this way, under suitable assumption of the values of fractional order nu, we obtained the integral version of Caputo fractional stochastic differential equation. Substantially, I refer to this SDE, to this integral equation with this G process, and at the end we can say that our Gompertz model can be constructed as a log normal process of y nu t. Indeed, the median of such a process is exactly the Gompertz curve proposed by Bolton et al. Indeed, it is solve this kind of fractional, this kind of differential problem when sine nu t, respect to which we are doing here the derivative, is a Mitter-Leffer function. And with the proposal to also to recover the Frunzo Gompertz model, we construct at first another process x nu t by composition of y nu t proposed here and psi function specifically chosen in this way, because this process has mean that is exactly the improved Gompertz curve by Frunzo, and it is solve this kind of problem proposed in Frunzo et al. But we are not satisfied because in this case we have that this process is not log normal. So we do a further step of generalization by which at the end we understand how to do in this second case. Now I give some definition, but this is the third time today about this definition. So I rapidly say that we consider Bernstein, already said by Giacomo and Nicolai, Bernstein function, special Bernstein function when conjugate is again Bernstein function. We jump the Levin-Kinchin representation also for the we want to say that we have the corresponding Levy measure, and we focus on complete Bernstein function, but in particular on this particular setting, which are the Bernstein function we consider are complete and with infinity mass by Levy measure, and we consider the bar nu, that is the tail of Levy measure. So we consider this the corresponding subordinator when we choose phi as Bernstein function. Its inverse subordinator with the absolutely continuous with the probable density phi. We also consider the potential measure of the given subordinator corresponding to Bernstein function phi, and its density. Little u phi, the potential density, adding also an assumption. This assumption is useful to give the existence and also to discover the beta Helder continuity of path of solution of the process we are constructing. we need again to recall the fractional integral of first type that is constructed by using the potential density U phi, indicated by I phi, and the second kind in which we construct a fractional integral induced by phi by using the tail of its Levy function, not its map, but the Levy function of its conjugate. And we discovered that when phi is the identity, we recover the classical integral. From the second definition of the second form of the integral, we are able to introduce also the definition of Riemann-Wheel derivative induced by phi function, and there is here the connection with the integral induced by its conjugate, and also Caputo derivative, in which the derivative induced by phi is in this connection with the integral induced by its conjugate. And about the inversion, as you can see in certain to Aldo, there is the motivation for which we consider the construction of the fractional integral by using the potential measure, because we can do the inversion by using the Caputo derivative just introduced here. It is possible also in this case to consider the fractional integral induced by phi and with respect to another function psi. So we use this kind of notation, recalling phi and psi, and as you can see, again we adopt the tail of Levy measure induced by the conjugate of phi, and the psi is involved, as you can see in this way in 22 equation. And the Riemann-Wheel derivative respect to psi again has this construction, as you can see, and this is the relationship with the corresponding fractional integral induced by the conjugate of phi, and again respect to psi function. And also for Caputo derivative, again we consider the Caputo derivative induced by phi function and respect to psi. As you can see, we can adopt a less heavy condition of phi, of phi and f, and more not on f. There is here the relationship with the corresponding fractional integral. At the end, in the operative way, we can consider now a couple of two Bernstein functions, phi1 and phi2 in the suitable set, and consider the generalized fractional problem connected with the Gompertz model, in which the couple of fractional equation involved the first one, the Caputo fractional derivative induced by Bernstein function phi1 respect to yt function, that is a solution of the second equation, in which the differential operator is that of Caputo induced by another Bernstein function phi2. Because in this way, we, in a more general way, write the solution, the rate function yt is written in terms of eigenfunction of fractional Caputo derivative induced by phi2 Bernstein function, and xt is the eigenfunction induced by phi1, eigenfunction of Caputo fractional derivative evaluated on yt. We also are able to show that yt is the logarithm induced by phi1 as the inverse function of the corresponding eigenfunction, because under our assumption we can prove that the eigenfunctions are strictly increasing function. And coming back to the original problem, when the Bernstein functions are related to stable subordinator, we have that specifically we have lambda to alpha I with the alpha I fractional order is in 0, 1. And specifically, we found this kind, we can construct this kind of fractional problem where we specialize the derivative here as that of Caputo of order alpha 1 respect to yt, and yt solve this one. At the end, we have the solution that has the advantage to unify the vision of the approach of Bolton and Frunzo and obtain the Gaussian curve, the Gompertz curve as a Mittag-Leffler function, because the eigenfunctions now are exactly the Mittag-Leffler over the alpha 1. Looking at the first equation applied to yt, that is written in terms of again eigenfunction, but also in this case we have a Mittag-Leffler function of order alpha 2. In the stochastic counterpart, this means that the stochastic process can be constructed starting with the yt process involving the integral induced by phi 2 and an additional Gaussian process gt with 0 mean. And constructed at the end the Gompertz model as the eigenfunction induced phi 1 of the modus of such a process and with parameter that depends on the signum of yt. In such a way, we can say that xt is log phi 1 normal process. It is a non-negative process, so suitable for describing the population dynamics. And in particular, calligraphic M, capital M, its median is such that can be recognized as the eigenfunction induced by phi of the mean of yt process. And finally, we can claim that the couple of a medium of xt process and the mean of yt process is the unique solution of this fractional deterministic model. We want at last recover the improved Gompertz curve, recognize that phi 1 has to be lambda to alpha 1, phi 2 has to be the identity. The corresponding differential problem constructed in Frunzo is exactly this one. We construct in the stochastic context the xt process in this way. Bang yt, the integral obtained by the classical integral and with the additional Gaussian process, and the median of such a process constructed by using the eigenfunction induced by lambda alpha 1 and evaluated in the mean of yt process at the end is exactly the Frunzo, the improved Gompertz curve proposed by Frunzo, recognize that when alpha 1 is equal to nu, this eigenfunction is exactly the Mittag-Leffler of new order evaluated in this rate function. These are some of the main references, but there are other lot. And in the two papers, these two papers, last two papers, in which are all the technical details of such study. And thank you very much for the attention.